Good afternoon. For the class DSI MGTS, I will be talking about the case University Toys and Business Professor Action Figures, presented by me, Lance Sobremonte. The case essentially talks about University Toys and their brand new line product, which is Business Professor Action Figures. An option the company can do is to ramp up production immediately while simultaneously launching an ad campaign. This would cost around $1,000. Based on past experiences, this could either do well or fail miserably. A unit is around $2 revenue. Again, there's a 50-50% chance where if it does well, it will be 2,500 units sold. When it does bad, it's 250 units sold. Another option that they can do is to test market the product. Again, it will earn $2 per unit sold as revenue. But products that sell well when fully marketed have also sold well in the test market 80% of the time. Meanwhile, products that sell poorly when fully marketed also sell poorly in the test market 60% of the time. So essentially, they have these two options. But there is a complication. A rival manufacturer rumored to be considering development of law school professor action figures is also appearing. The university decides to go ahead and ramp up production and fully market the business professor action figures. Doing so would still lead to $1,000. However, sales prospects depend on whether the law professor action figures has been introduced to the market or not. Essentially, we will be talking about these factors and how University Toys can do management well for their business professor action figures line. Suppose that the test marketing is done. Use the posterior probabilities template to determine the likelihood that the BPAF would sell well if fully marketed, given that it sells well in the test market and given that it sells poorly in the test market. So essentially, we have the states of nature, which is does well in the test or does poor in the test, does well in the full market or poor in the full market. As mentioned before, there is a 50-50% chance. That's why it is zero point 0.5 and zero point 0.5. Furthermore, that we know it will do well in the test 80% of the time, thus zero point 0.8. But we also know it will do poor in the test zero point 0.6 or 60% of the time. Thus, we have these values. So we got zero point 0.8 and zero point 0.6. So essentially, how we got zero point 0.2 is 1 minus zero point 0.8, and how we got zero point 0.4 is 0.6, 1 minus zero point 0.6. For the posterior probabilities, we have finding and p finding and the states of nature. To get p finding, the zero point 0.6 is essentially zero point 0.5 times zero point 0.8 and zero point 0.5 times zero point 0.4, and we multiply those values. Thus, you will get zero point 0.6. Furthermore, to get the 0.666667, what we do is we get zero point 0.8 times zero point 0.5 over zero point 0.6, which will lead to 0.667 or 66.67% of the time. To get the 0.75, what we do is zero point 0.6 times zero point 0.5 divided by zero point 0.4, and it will be 75% of the time. We also, to get the 0.333 is essentially 1 minus 0.6667, and to get the 0.25 it is essentially 1 minus 0.75. Next, we need to create a decision tree to help University Toys decide the best course of action and the expected outcome. From the previous table, from the posterior probabilities, we know all of the percentage chances. So zero point 0.8, zero point 0.4, zero point 0.2. So essentially, if it tests well or sells well, it is zero point 0.8. Thus, we can see the line at the very top. So if it tests, so we can test well minus sell well. So it's zero point 0.4 times zero point 0.8 equals 0.32 divided by 0.56, which is 57.14, which is 57.14% chance at the time. Furthermore, following the same line, we can see test poorly minus sell well. That is a zero point 0.4 times zero point 0.2, which is 0.08, and it is 0.08 over 0.44 or 0.1818, or 18.18% chance. Furthermore, we know it can also test well slash sell poorly. Thus, test well minus sell poorly is zero point 0.6 times zero point 0.4, which is 0.24. 0.24 times 0.54 equals 0.4286 or 42.86% chance. Meanwhile, it will sell poorly So it will test poorly slash sell well. So test poorly minus sell well is zero point 0.6 times zero point 0.6, which is 0.36. So 0.36 divided by 44, which is 82.80, 0.8282, which is 82.82% chance. So you can see by the p-test well equals 0.32 plus 0.24 equals 0.56. Meanwhile, p-test 40 is 0.06006 plus 0.36 is 0.44. So what is the best course of action and the expected outcome? The best course of action is to skip the test market entirely and immediately market the full product fully. The expected payoff is $1,750. Now, suppose that the university choice is uncertain of the probability that the law school professor action figures will enter the market before the test marketing would be completed. If it were done, how would you expect the expected payoff to vary as the probability that the law school professor action figures will enter the market changes? If the probability of the law school professor action figures enter the market before the test marketing would be completed, it would it would make the test market even less desirable. So it would still not be worthwhile to do so. Essentially, if it enters, it is essentially a hindrance to university toys, and it would not be worthwhile to pursue this. However, if the probability decreases, it would make the test market more desirable. It might even reach the point where test market is worthwhile. So essentially, if the law school professor action figures enter the market, it gives less time for university toys to pursue the business professor action figures. So they need to push it quickly before the law school action figures can come out. Next, we need to generate data, the data table that shows how the expected payoff and the test market decision changes as the probability that the law school professor action figures will cater the market varies from 0% to 100% at 10% increments. So essentially, what is the percentage chance or the expected payoff, and if we should test market it based on the percentage chance that the LSPAFs will cater to the market. So based on the percentage chance, as we can see here, there is a pattern. From at 0%, the test market is no and the expected payoff is 1975. Meanwhile, at zero point 0.1 and zero point 0.2 at 10% or 20% chance, it is likely that it would be more profitable to do the test market with the expected payoff at 1960 and $1755. Going beyond that at 30%, 40%, all the way to 100%, it is a no and it'll constantly stay at 1,755 expected payoff. Lastly, at what probability does the test market decision change? Essentially, as said previously, it is better to perform the test market at the probability that the LSPAF enters the market at 10% or less. It is better to skip the test market if the probability is greater than 10%. So essentially, if it goes beyond 10%, it becomes a detriment if you want the highest expected payoff, because essentially you can still do the test market at 20%, but it will be the same expected payoff as going the percentage chance after that. So that is it for the business professor action figures case, and we hope that this will be able to help you understand better the expected payoffs and the percentage chance and the probabilities and the best possible solution management can do for this case. Thank you.